Hello, everyone. Good evening. So, in today's session, we will be discussing the previous year gate problems from the year 2017 from the aerodynamics piece. So, let's get started. Mhm. So, the distribution of the questions looks something like this. So, you have around two 1 mark questions and then around four 2 mark questions. So, that's totally making it around 10 marks from the aerodynamics portions. And let's get started. So here, what they're asking, which one of the following statement is not true? So they're asking which is false. All right. So the first statement is the pitching moment of any airfoil at any angle of attack is always zero at the center of pressure. So which is a true statement, right? Because your center of pressure, so if you take any airfoil, center of pressure is supposed to be the point where all the forces, the resultant of all forces act, right? And if that is the point where the resultant force is acting, then there cannot be any moment over here, right? That is, moment at the center of pressure will essentially be zero. So this is a true statement, all right? The pitching moment of any airfoil at any angle of attack is always zero at the aerodynamic center. So this is basically a false statement, right? Because aerodynamic center, the only condition that it needs to follow is that the moment is independent of angle of attack. In some cases, it can be zero, but not always, right? So moment at the aerodynamic center, MAC, is just that it is not a function of angle of attack, alpha, but doesn't mean that it will be always zero. So this is a false statement, right? And they're asking which is the false statement out of it. So the right answer here is option B. But let's examine the other options as well. In option C, what they're asking is the center of pressure and aerodynamic center coincide for a symmetric airfoil, which we have seen from thin airfoil theory that uh, for a symmetric airfoil, what happens is that the center of pressure and aerodynamic center, they coincide because when we calculate what is the MAC, the moment at the aerodynamic center for a thin symmetric airfoil, it comes out to be around uh, zero. So which basically means that your aerodynamic center is nothing but your center of pressure. So which this statement is again true. The pitching moment about aerodynamic center for any airfoil does not vary with angle of attack, which again is the definition of the aerodynamic center, right? Because the moment at the aerodynamic center is independent of the angle of attack. This is also kind of true. So the right option here is pitching moment of any airfoil at any angle of attack is always zero at the aerodynamic center, which is a false statement. So the right option here is option B. All right. Any questions on this? Go to the next. Which one of the following statement is not true? Again, they're asking a false statement. So let's look at all these statements. Compared to a laminar boundary layer, a turbulent boundary layer is more desirable on a wing operating at large angle of attack. All right. So what they're saying is that you would like to have a turbulent boundary layer if your wing is acting at large angle of attack, which is kind of true because at large angle of attack you are more susceptible to flow separation and stall, those phenomena. So if you have a turbulent boundary layer, the flow separation will happen a bit delayed. So your the flow separation related drag or the drag, the pressure drag in such cases will be lesser. So this is actually a correct statement that we actually desire a turbulent boundary layer. Option B, the skin friction drag for a turbulent boundary layer is larger than for the laminar boundary layer. This is again true, right? Because the skin friction is higher because of the eddy viscosity for a turbulent boundary layer. And the only thing is that the turbulent boundary layer will remain attached for a longer period of distances than a laminar boundary layer. But the skin friction is definitely going to be higher. So this is true. The location of transition of laminar to turbulent boundary layer depends only on the operating Reynolds number. All right. So this is actually a false statement. The reason being, um, the what they're saying is that only whatever the Reynolds number in which you're operating is the only factor in deciding where your transition from laminar to turbulent boundary layer will happen, which is actually not true. So this will actually depend upon a bunch of other things like um, in some cases it can depend even on your on your dimensions of your body, and most importantly, it'll depend upon how rough or smooth your surface is. Like for example, um, mm, in case you have a very rough surface over which your flow is moving, a laminar flow is moving, it'll become turbulent much faster. It'll become turbulent much earlier than on a let's say if you have a very polished and smooth surface, um, then the flow separation will be quite delayed. So let's say you have a very rough surface, let's say a lot of spikes on the surface, and then you have a smooth surface. Both are operating at the same Reynolds number, um, RE, RE. So your transition to turbulence will over here will happen earlier as compared to in the smooth case, because you're providing a lot of disturbance to your flow, which will then grow and then eventually become turbulent. In this case, there are much lesser disturbance, right? So Reynolds number is not just the only deciding factor over there. Option D, so the right option in this case, the not true option is option C. And if you look at the last option, a separated flow does not necessarily lead to a turbulent layer, which is basically another true statement that even if you have though you have might have flow separation doesn't really mean that you have a turbulent boundary layer, because maybe a flow is laminar and then it separates and then it creates the wake. Doesn't it creates a turbulent kind of a flow feature? Basically, um, it can create a lot of eddies or region of wake, which is a region of reverse kind of flow as we speak, in the wake region or in the region where there is flow separation, but there's no bound layer as such over there. There is no bound layer which is attached to your body and which is turbulent, in case in that case. So there's no guarantee that you'll always have a turbulent bound layer once the flow separation basically occurs. So this is kind of true. Can you explain the third option? So the location of transition from laminar to turbulent bound layer depends only on the operating Reynolds number. So Reynolds number is so the transition to laminar to turbulent. Basically, at what distance? Let's say you take a flat plate. How much distance from the leading edge should I go uh, for this transition to basically occur? Is what they're asking. And would it depend only on the Reynolds number, whether if the Reynolds number is 10 power 5, 10 power 6, or whatever? But we know as a fact that it's not just the Reynolds number. Reynolds number is a very important factor, but it's not the only factor. There's another important factor called as the smoothness or the roughness, how rough or smooth your surface is. Because let's say you take a very smooth flat plate, a very rough flat plate, and a very smooth flat plate, and you let your flow pass through with the same Reynolds number, right? But in this case, you have a lot of roughness, so it will create a lot of disturbance in your flow field, and that disturbance will grow, and the transition will happen early. Much sooner it will happen. Let's say maybe 10 centimeters from the leading edge. I'm just giving a random number, all right? But in this case, since the surface is much smoother, there is very little disturbance that goes onto your flow. Maybe in this case, the transition will happen maybe 20 centimeters from the leading edge. So it's not only, and both are operating on the same Reynolds number. So it's not just the distance from the leading edge, it's also how much smooth or rough your body is. That also makes a difference. Okay. Any other questions on this? Let's go ahead. So in this question, consider a straight wing with rectangular planform of aspect ratio 10 with an ACA 0012 airfoil. The span effectiveness factor for this wing is 0.95. Assume the flow to be incompressible and governed by thin airfoil theory. The lift coefficient of this wing at an angle of attack 6 degrees is. So what they're saying is that you have a wing which is a rectangle planform, because which means that your all the chord lengths along you have the same chord length along every span-wise location. The aspect ratio AR here is 10. All right, it's a NACA 0012 airfoil. So and then they've asked us to consider the flow to be incompressible and gone with thin airfoil theory. So and we know that NACA 0012 is a symmetric airfoil. And if you were to estimate its lift curve slope, it would be somewhere around 2 pi per radians. Right? That would be around 2 pi would be the value of lift curve slope for a thin for a typically thin symmetric airfoils. And they've told you the span effectiveness factor is let's say E around 0.95, because there would be some efficiency losses because of having non-elliptical planform, right? So that is this factor. Now what they're asking us is, what is the lift coefficient of this wing at an angle of attack of 6 degrees? So alpha is 6 degrees, all right? And if I convert that to radians, this would be 6 into pi by 180, right? So many radians. Now they're asking us not just the lift coefficient of the airfoil, they're asking you the lift coefficient of the wing. So we know that from Prandtl's lifting line theory, whenever you have a wing which is made up of an airfoil, the lift coefficient of the lift curve slope of the wing is related to the lift coefficient of the airfoil that makes up the wing by this relationship, right? And by uh, I'm sorry, not divided by pi into aspect ratio times the efficiency factor. So we know that because of your induced drag effects, because of your induced velocity, there will be a reduction in your lift curve slope, and that reduction in lift curve slope for the entire wing, basically. So if you start with the lift curve slope of your airfoil, you can find the lift curve slope of your wing using this relation, and this change in the lift curve slope is primarily due to your induced velocity and those effects. So you know what is your lift curve slope of your airfoil, because they've told you it's a symmetric airfoil, and you can typically estimate the lift curve slope of a symmetric airfoil as 2 pi. And you know the aspect ratio, which is 10. You know the span efficiency factor, which is 0.95. So if you were to calculate your if you were to just substitute the values over here, so that would be around 2 pi divided by plus 2 pi into pi into aspect ratio is 10, and then the span efficiency factor is around 0.95. All right, so this would be your A, that is your lift curve slope, and then this would you would estimate this to a value of around uh, Should be around 5.19 per radians. Keep in mind, everything needs to be in radians. So whenever you're doing any calculation, always convert everything in the form of radians and then proceed with your calculation. All right. And finally, to find the lift coefficient, which is nothing but CL, and that will be nothing but A into alpha. So it's a symmetric airfoil, so it does not have any zero lift angle of attack. So this would be just A times alpha. And so this is nothing but A is 5.19 and alpha is, in our case, 6 into 5 by 180. All right. So CL in my case, this would turn out to be around a value of 0.54. That would be the CL value. And this is for the entire wing, not just the airfoil. All right. Any questions here? So moving ahead, consider an incompressible flow over a flat plate with the following approximation to the velocity profile. So there is a flat plate, all right, and there's a flow over the flat plate, and there is a boundary layer formation. So they're saying that within the boundary layer, y less than delta, less than or equal to delta, which is this region, they're telling you that the velocity profile u by u infinity, which is capital U here, is nothing but y by delta. And beyond the boundary layer, we know that the velocity is nothing but u equals u infinity. So u by u infinity is nothing but 1, right? That's basically what they're giving us over here. And delta is the boundary layer thickness, use of free stream speed. The normalized momentum thickness, theta by delta for this profile is. So what they're asking you is, what is your theta? All right. And theta, you know that from boundary layer theory, is defined by the integral 0 to delta uh, cap small u by u infinity. So u by free stream velocity capital U into 1 minus small u by a free stream velocity whole thing into dy, right? And that's basically where you need to figure out as well what is your theta, and you know what is the expression for u by u infinity. It's already given in the question. So let's just go ahead and calculate this integral. Theta equals integral 0 to delta y by delta into 1 minus y by delta into dy, right? So let me just multiply everything inside. Y square by delta square into dy, right? So this again, if I were to do the integration, it would look something like this. This would become y square by 2 delta. And this would be y cube by 3 delta square. 0 to delta. So this would be, so if I were to substitute delta and 0 as the limits, this would be delta square by 2 delta minus delta cube by 3 delta square. So this gets cancelled. Delta square, this gets cancelled. So this will be delta by 2 minus delta by 3, just nothing but delta by 6, right? Another question they've asked you for what is the normalized momentum thickness, which is delta by theta by delta. So you know theta is delta by 6, so theta by delta will be nothing but 1 by 6. All right, so it should be around 0.1 into 6, 6, 6, and so on. All right, just a very simple integral that you need to evaluate, and you have the answer. Any questions? Okay, go ahead. An idealized velocity field is given as v equals 4txi minus 2t square yj plus 4xzk. At point -1, 1, and 0, and at time t equals 1, the magnitude of material acceleration vector of the fluid element is. Right. That's basically a simple problem which is giving you the velocities and asking you to calculate the acceleration. All right. So you have your x direction velocity u as 4tx, your y direction velocity as minus 2t square y, and your z direction velocity is 4x z. All right. And they're asking what is the material acceleration. So acceleration is nothing but dv by dt, right? Your material derivative for that matter. So you need to calculate what is the acceleration in x, y, and z direction. All right. So acceleration in the x direction, which is nothing but the small u by dt, is nothing but the time derivative, local derivative, the local term plus the advection term, which is nothing but u into dou u by dou x plus v into dou u by dou y plus w into dou u by dou z. All right. So just need to evaluate these terms to find ax. So dou u by dou t is nothing but derivative of this with respect to t, which is nothing but 4x. All right. Plus u into dou u by dou x. So u is 4tx, dou u by dou x is 4t. All right. 4tx into derivative with respect to x is nothing but 4 times t. All right. Plus v into dou u by dou y. So v is minus 2t square by y, dou u by dou y. U is not a function of y, so this will basically be 0. And then we have w into dou u by dou z. W is so much, but then again u is not a function of z, so this goes to 0. Right? So that is ax. And if you were to evaluate your ax at the point which they have mentioned, where t is equals 1, x is minus 1, y is 1, and z is 0, so you would find your ax to be around the value. So if I substitute 4 into minus 1, that's minus 4, plus 4 into t is 1, x is minus 1, into 4 into 1, so that is nothing but minus 16. When I sub, so the t is 1, x is minus 1, and t is 1 again. So substituting that, I get minus 16. So your ax would be nothing but minus 20 meter square per second, meter per second square, right? So this is your ax. Now let's calculate what is my ay. It's nothing but dv by dt. All right, that is nothing again, same thing as earlier, but just with v in all the derivatives. Dou v by dou t is u into dou v by dou x plus v into dou v by dou y plus w into dou w by dou v by dou z. Right. Now let's evaluate these integrals, these derivatives. So dou v by dou t is nothing but minus 4ty. Because my v is minus 2t square. If I do the derivative, will be minus 4ty. And next is u into dou v by dou x. U is so much, but v is not a function of x, so this term basically goes to 0, right? Then we have v into dou v by dou y. V is minus 2t square y, and dou v by dou y is nothing but minus 2t square. All right. W is 4xz, and into dou v by dou z, and but v is not a function of z, so this also becomes 0. All right. If I were to evaluate my ay for the point x minus 1, 1, 0, and t equals 1, so this would be t is 1, y is 1, t is 1, and y is 1, t is 1. So this would be nothing but minus 4, and this would be minus 2 into minus 2, which is plus 4. So minus 4 plus 4, which would be nothing but 0 meter per second square. All right, that would be your acceleration in the y direction. Now let's calculate AZ. AZ is nothing but dw by dt is nothing but dou w by dou t plus u into dou w by dou x plus v into dou w by dou y plus w into dou w by dou z. So dou w by dou t, let's go back. Dou w by dou t, w is not a function of time, so that basically becomes 0. Then you have u into dou w by dou x. Dou w by dou x is nothing but 4z, and u is 4tx. So this would be 4tx into 4z. All right. And then you have v into dou w by dou y. Your w is not a function of y, so this would basically be 0. And then you have w into dou w by dou z. So w is 4xz, and dou w by dou z is nothing but 4x. So 4xz into 4x, right? And if I substitute the value of x and t and y and z, so z is 0 and t is 1. So if I substitute z 0, this term, so z is 0, so this term becomes 0, And here again, z is 0. This term becomes 0. And the other values of x and t, whatever they are, doesn't really make a difference, right? So az is again 0, right? So many meter per second squared. And in the question, they're asking you what is the magnitude of the material acceleration. So you found ax to be -20, ay to be 0, and az to be 0. So the magnitude of acceleration is nothing but square root of ax square plus ay square plus az square, right? So in this case, we have ay az 0. So this would be nothing but magnitude of ax, which is nothing but 20. So we don't have to worry about the sign because in the question, they've only asked you what is the magnitude, right? So minus 20 is basically 20 meter per second square is the answer for this. Here, everyone, any questions? This is quite lengthy, but very, very simple problem. Okay, continue. A football meant to be thrown at 100 km per hour in sea level with the density and viscosity of air at sea level is given is to be tested using a 1/4 scale model in water tunnel. All right. So you have a football which is actually supposed to be working at sea level, and it is supposed to be it's supposed to have a velocity of 100 kilometers per hour. But now to test it out, what they're using is a 1/4 scale model. All right. So let's say if your prototype is the football that is supposed to be at sea level, so the density of air in the prototype case would be density at the sea level, which is 1.22 kg per meter cube. Viscosity of the prototype in this case is again 1.78 into 10 power minus 5, right? 10 power minus 5. And the velocity of the prototype is 100 kilometers per hour. So you can just multiply it by 5 by 18 and convert it to meters per second, right? So you have these information, and let's say your the diameter of the prototype is, let's say, d. All right. Then you have the model, which is supposed to be tested, right? Now the density of the fluid in the model scenario is water. So that is the fluid is water. So the density that density of fluid that my model will see is 1000. Viscosity of the fluid in my model is basically -3. All right. And it's a 1/4 scale model. So the diameter here is nothing but d by 4. All right. Now, what they're asking is the ratio of the model force to the prototype force. So let's say whatever the force that my model is experiencing, uh, you need to divide that with the force that my prototype would experience. So whatever is a smaller scale version, how much force is acting on this divided by how much force is acting on my prototype. All right. So we need to use a dimensional analysis over here. So first we need to enforce the Reynolds number similarity, right? The Reynolds number should be same for both. All right. So if I enforce Reynolds number similarity, dynamic similarity over here, so Reynolds number of my model should be equal to Reynolds number of my prototype. All right. So which means that rho model, V model, diameter of the model, which is d by 4, into viscosity of the model, viscosity of the fluid in the model, is equal to density of the fluid in the prototype, velocity of the prototype, diameter of the prototype, which is d, let's say, and viscosity of the prototype mu. So you have all these, you have rho m, you have d anyway, will get cancelled on both sides. You have mu m, you have mu p, you have rho p and vp. The only thing to calculate here is velocity. With what velocity should the fluid be going over my model? And if I substitute my rho m as 1000, Vm is so much, which we need to find. Mu m is 10 power minus 3, right? And then there is a 4 in the denominator. That is equals density of the prototype, the density of the fluid in the prototype, into velocity is nothing but 100 into 5 by 80, right? 80, and then the viscosity, which is 1.78, 10 power minus 5. Now, so if you were to do this calculation, your velocity of the model will turn out to be around the value of 7.615 meters per second. All right, this would be the velocity of the uh, fluid in the case of a model. All right, but our question is how to find the ratio of the model and the prototype force. So we know as a matter of fact that if there is similarity, the non-dimensional coefficients like this force coefficient on the model will be equal to the force coefficient on the prototype, right? We know like the non-dimensional quantities like CL and CD or any kind of forces, their coefficients are going to be the same if there is similarity, but the actual value of force might be different, right? So that basically means that, let's say if I were to write this CF and CFP in terms of the forces, so CF of the force, coefficient of force on the model will be nothing but force on the model divided by half density of the fluid in the model scenario, velocity of the fluid in the model scenario, and then area. Uh, so the area will basically be, let's say, if you were to consider your football as a sphere, your area would be nothing but, let's say, surface area. If you were to take, let's say that would be around 4 pi uh, r square, right? So, so in this case, so whatever is the radius, right? So let's imagine we are taking the total surface area. So it basically scales, or your area would scale as, if I were to convert this to my, in terms of my diameter, um, we know that this would be, let's say, d by 2 square. Um, so so we know that the area would basically scale as diameter square of the diameter, and rest everything would basically remain the same, right? So in this case, it would be nothing but let's say, let me write it as 4 pi into diameter of the model square by 2 square. All right, and that is equal to nothing but force on the prototype divided by half density of the fluid in the prototype, velocity of the fluid in the prototype, into 4 pi into diameter of the prototype by square by 2 square, right? So, this 2 square, 4 pi, they'll just get cancelled. Half will gets cancelled. Now, what you need is the force on the model to the prototype, right? So, Fm by Fp is what you need. If I take Fm by Fp to one side, and you know that the diameter of the model is nothing but d by 4. If dp is equals d, prototype is d, diameter of the model is nothing but d by 4 for that matter, right? So I'll substitute all that. So I have rho m v m square into diameter of the model is d by 4 square divided by rho p vp square into diameter square. So substituting the values, so rho m is 1000, velocity in the model is around 7.615, square of it, d square will get cancelled. So you have rho p is 1.22, velocity in this case is 100 into 5 by 18 whole square into, and then the 4 square, which is nothing but 16 in this case. So 16, so which I need to write that as well. So if you were to calculate this would turn out to be around close to a value of 4. The force on the model to force on the prototype, right? So that is basically what they want, ratio of the model force to the prototype force, right? That's basically how you would do this problem. Any questions on this? So yeah, that is the last problem that we have in the 2017 paper. Yeah. So all these questions, as you can see, are quite easy, and even the very easy questions like might be a bit lengthy in some cases, but they're quite easy. So if you uh, uh, just be very meticulous on your steps, I think it should be very straightforward. Right. Okay. So that's all I had for today, guys. Thank you for joining in. I'll see you, in our next session.